I'm Mike Huckman at the Bio Buzz Center, and it is a pleasure to welcome Dr. Kate Rubins, who, as you might tell, is an astronaut and a biologist. Thanks for being here.
Yeah, absolutely. It's a pleasure.
So it was about this time last year that you were getting ready to go into space.
I was, yeah. We were getting ready to launch from Kazakhstan, which is where we launched on the Soyuz vehicles. And so I was actually in quarantine this time last year before we launched July 7th, the space station.
So you went into the space station for, 3 to 4 months, and one of the things you did up there is you became the first person in the planet and off the planet to sequence DNA in space. Why in the heck did you do that, and what did you learn from it, if anything?
Yeah, that was exactly my question when the researchers came to us a few years ago and said, we want to send a sequencer to space. And I said, why would you bother doing that? Why wouldn't you just send your sample back to the planet? And the question really is, when we start to do exploration class missions, when we start to leave Earth's orbit for a long period of time, we're going to need to do in situ kind of point of care analysis.
Which means?
Which means right at that moment when you're in space, you need to be able to get some data back instead of waiting to return the sample to Earth. So there's a lot of reasons that you might want to use sequencing as a platform. So the reason we launched this sequencer really was a technology demonstration. We wanted to see, could we get sequencing to work? Would there be technological hurdles? And would this be a useful technology, for example, to study the microbiome, to study a biomarker of bone loss and disease as you're getting further and further from Earth? And it works. That's the bottom line, actually, is that the technology worked with very few hiccups, and we've now progressed in our next phase of experiments to going from environmental samples. So we can take a swab on the inside of space station and actually go from that, do the library prep, and get the sequence right away, right there, without having to send any sample back to the planet.
Really cool. So Kate, is there additional applicability, though, from research that's done in either no or little gravity for those of us who are earthbound?
Yeah, absolutely. And you wouldn't necessarily make that connection. Why would you want to do research in space? Really, it's the fact that we get access to gravity as a variable. So all of our experiments that we've done on the ground have always had 1G. We've never really been able to play with gravity as a variable. What we can do on the space station is actually look at microgravity. So we have almost no gravity. The experiments are in free fall, the research laboratory is in free fall, the experimenter is in free fall. And so we can actually look at things like materials properties, lack of different currents in materials, differences in sedimentation, where you won't have things necessarily falling to the bottom of a plate when you're plating tissue culture cells.
Fascinating. So before you became an astronaut, you were a well-established researcher, primarily in infectious diseases, and you did a lot of work with infectious diseases in poor countries, and more specifically in Africa. There's a lot of talk about helping the developing world with public health, with healthcare, etc. What could or should biopharmaceutical companies like the ones who are gathered here at this convention be doing that they're not doing today?
I think when we think about our technologies, we generally tend to assume that they're going to be US-based or Western medicine-based. We're going to have power available to us. We're going to have massive amounts of data and internet connectivity. We build our instruments to be benchtop based and not necessarily translatable to a rural area. And so we actually find a lot of those same challenges when we're building something for a space station research environment. We're solar powered entirely up there. We have limited data bandwidth. We have to think about the quantities of materials. Are they refrigeratable or not? And so as folks are developing technologies, as they're developing diagnostic assays, any kind of equipment or device, if you can make it portable, if you can say, how would this not depend on a stable power grid? How could we make this device work in a really rural outbreak situation? Those kinds of things are great for off-world exploration, but they're also very pertinent to doing outbreak research, for example, in central Congo.
And not treating it as an afterthought or as something they need to think about in a case of an emergency.
Yes, if it comes along as part of the development process, is there a way to make this technology accessible in a remote environment? That actually goes a long way to immediately translating into good medical care or something that we can use for a diagnostic.
Kate, the theme of this year's BioConvention is the word breakthrough. To your mind, from where you stand, breakthrough to what would you like to see a breakthrough to?
I'd like to see a breakthrough to exploration. I want to see us continuing to get farther and farther away from our planet and learning how humans can survive in outer space and how we're breaking through to exploration.
That's Dr. Kate Rubins, NASA astronaut and biologist, here at the BioBuzz Center.